Welcome back to this Forge College Explainer. Okay, so we're pivoting today. We're stepping out of that little detour we took into Solana and the .cloud directory, and we are jumping right back into the deep end of Ethereum EVM optimization. We're officially in the capstone module of our EVM deep dive on execution and environment, specifically analyzing execution flow. It's time to take all those raw, chaotic EVM execution traces we've been gathering and, well, transform them into beautifully standardized, actionable blueprints. Let's get into it.
Here is our blueprint for today. We're going to cover our EVM return, dissect the anatomy of optimization cards, design some flowchart stencils, hit the assembly process, pass a strict validation checkpoint, and then wrap up with your next steps.
So Section 1, Introduction and our EVM return. Look, we survived the Solana wilderness, right? But it's time to focus strictly on Ethereum again. Tossing undocumented random ideas at a codebase, it's literally like building a spaceship without a blueprint. Sure, you might get off the ground, but you're probably going to explode in orbit. We're moving completely away from chaotic, trust me bro, developer comments. Instead, we're shifting toward a rigorous, patent-like documentation standard. Gas optimization is an exact science, and we need to treat our findings with serious engineering respect. And the ultimate artifact for this rigorous approach? It's the optimization card. Think of it as this concrete, patent-style blueprint drawn out on beige paper that bridges a bottleneck you've identified in an EVM trace with a measurable, deployable solution. It completely removes the guesswork. Every single card holds the context, the root cause, the exact steps to mitigate the issue, and, most importantly, the criteria to actually prove that your fix saved gas. All right, Section 2. Let's look at the anatomy of optimization cards. We really need to treat these cards like strict technical spec sheets. Every card starts with 4 foundational fields. Your title, it needs to be a short, action-oriented phrase, penned in crisp, dark green ink. Then there's the scope and trigger, which absolutely must point to the exact code path and trace IDs, mapping your card to hard, undeniable evidence. Next up, your root cause. This is a concise diagnosis of the specific EVM opcode that's bleeding gas, like, say, a repeated SSTOR in a loop. Finally, mitigation steps. Provide an ordered, highly actionable checklist to fix that exact issue. Now, the second half of your card demands hard estimates and concrete test plans. We need estimated effort, low, medium, or high, just for resource planning. Expected effect is your measurable success criteria, like a specific percentage of gas reduction. Validation tests outline the exact benchmarks to run so that success is fully verifiable. And finally, references. Listen, this is absolutely non-negotiable. You must link back to your annotated trace IDs for rapid cross-checking. Just look at the contrast between a vague, completely useless suggestion and a highly specific entry. Writing something like, fix the gas in the contract is a total nightmare for whoever inherits your code base. I mean, where do you even start? But a precise entry, like batch SSTR writes in contract A's update all function, now that is an actionable title that a developer can immediately understand, trace, and implement. Honestly, it's night and day for the engineering workflow. Moving on to Section 3, Designing Flowchart Stencils. So a stencil is essentially the visual counterpart to your optimization card. When you're staring at a massive execution flowchart, you really don't want to be reading dense paragraphs of text, right? You want clear, technical symbols. The stencil defines the shape, the visual hierarchy, the connector semantics, and the annotation rules to keep your diagrams perfectly readable and mathematically consistent across the entire board. Your stencils have to adhere to strict visual rules fitting our technical panesthetic. We need a shape taxonomy drawn in crisp, dark green, maybe a rounded rectangle for suggestion and a sharp badge for confirmed fix. We use priority glyphs, highlighted in bright orange, to instantly communicate if an effort is high, medium, or low. Connector semantics are vital too. A dashed line implies a potential mitigation path, while a solid line is the executed path. And everything exports as scalable SVGs so your architectural blueprint looks totally flawless. Okay, Section 4, the assembly process. Now that we know what our cards and stencils actually look like, it's time to hit the assembly line and build these artifacts step by step. Phase 1 is all about extraction. You pick your top 3 actionable bottlenecks from your prioritization matrix. Then, you draft the markdown template for your card, filling out all those mandatory headers we just talked about. And step 3 is absolutely crucial. Estimate the effort and calculate the expected gas reduction based entirely on your trace data. No guessing allowed here. The final assembly steps lock in your validation methods. You detail the exact tests to run to capture those before and after data points. Next, design your vector stencils so they map perfectly to your card fields. Finally, export and manifest. This is where you neatly tie everything together, your markdown cards, your annotated traces, and your SVG stencils, all into a single, machine-readable JSON manifest file. This is the exact package that your final flowchart is going to consume.
Which brings us to Section 5, the validation checkpoint.
Before we can even think about moving to the final capstone assembly, your artifacts must survive this checkpoint. When you validate your cards, you need to confidently state measurable data. If you claim, say, a 35% expected gas reduction, you can't just pull that number out of thin air hoping no one checks. No way. It must be backed by a dry run against your annotated EVM trace. You literally have to capture the before-state gas numbers, mock the expected change, and prove that the math actually works.
Use this peer review rubric to grade your work. Ask yourself, is the problem and mitigation clear? Are the steps actually actionable developer tasks? Are the tests measurable? And remember my absolute favorite mantra, traceability is non-negotiable. Every single claim must point to an exact trace reference. Finally, visual fit. Does your dark green and orange stencil snap perfectly to a flowchart grid? Pass this rubric, and you pass the checkpoint. Almost done. Section 6, conclusion and next steps.
I really love this quote from the source material. These artifacts convert analytical insight into reusable building blocks. Cards communicate what to change and why. Stencils communicate how those changes appear. By transforming raw EVM bottlenecks into these standard modules, you're basically ensuring that future maintainers can easily understand, validate, and actually build upon your architectural blueprints. You are finally thinking like a true systems engineer. So here is the final question for you. Are your optimization cards and stencils rigorous enough to snap seamlessly into an enterprise-grade EVM execution flowchart? Or are you still relying on that trust me bro engineering? Take the time to polish those JSON manifests and SVGs. Anyway, thank you so much for joining this Forge College Explainer. To master more Web3 topics and get fully prepped for your final capstone project, make sure you visit forge.college. Stop guessing, start documenting, and I'll see you in the flowchart assembly.